Hi there, I'm Stefan Lauwade, and welcome back to part 3 of my introductory series to C++'s standard template library. In part 1, we covered the overall view of the STL, including the sequence containers, vector, deck, list, and forward list. And in part 2, we looked at associative containers, map, multi-map, set, multi-set, the hash containers, and the erase remove idiom. And at the end of part 2, I gave you a homework problem to write a function template that would accept any STL container and erase elements according to the value or according to a predicate. This is very useful because STL containers, they all have very similar interfaces. They all expose begin and end iterators. So once you've learned how to use one, you've rapidly learned how to use the rest. But when it comes to erasing elements from them, they actually differ somewhat radically. So it's convenient to be able to hide all of this behind a wrapper function template so that when you're erasing from a vector, you don't need to type begin and end 3 different times. So a number of people submitted solutions in the comments. They were actually very good. I pointed out some problems in the comments. You can read them there, dealing with the nature of the template, parameters that you have. It's actually easy to get wrong if you haven't written this sort of stuff before. I've written up a solution here just to show you how I would do it. The thing about erasing elements is that there are sort of different families of containers. On the one hand, you've got a vector, which wants to use the erase remove idiom, as I explained in part 2. And deck, the doubly ended queue, also behaves like that. It's random access. It has the same behavior. Whereas list and forward list, they're different because they are node-based. They actually have member functions that will erase elements according to value or according to predicate. And what these do is simply snip out nodes that you don't like. It doesn't do any assigning of elements like vector and deck have to do. So while you can use the erase remove idiom with list and forward list, it is at least as efficient and potentially more efficient to call their member functions. And then finally, you've got the associative containers, which have a different way of erasing elements, and they actually have no member function to erase according to predicates. So you have to write that with an iterator loop. So to show you how I would do it, because there are these 3 different sort of families of containers as far as erase is concerned, I am going to first include all the headers that I need, including the algorithm header for erase remove, and then all the headers for the containers. Then I'm going to be providing my function template in some namespace. This would be sort of my projects library namespace. In this case, I'm just calling it meow. And then I'm going to need some helper machinery. I'm going to put that in a namespace detail. Here I'm just compiling a CPP file, but in general, I would be putting this in a header. Headers should use namespaces to avoid stomping on other code. And in particular, they should not use unnamed namespaces. There's an obscure gotcha there relating to the one definition rule. The usual practice is to use detail namespaces. The idea is if you say namespace detail in a header, people outside your library maintenance team should not be referring to stuff in that detail namespace. So you can think of it as like unnamed namespaces in CPP files or static if you're used to C. Then I've got a little bit of machinery here that resembles the iterator traits and iterator category machinery from the STL. The STL doesn't provide this for containers, but we can provide it ourselves. So I've got some empty structs, which I've named vector-like tag, list-like tag, and associative tag. And I'm going to have a helper struct called container traits that is templated on a container and will return me what category this container falls in. This is a simple example of what's referred to as template metaprogramming. What this means is you're writing templates to do a little bit of computation at compile time. In this case, we're computing something based on the type of a container. We're trying to figure out what category it belongs to. And we have to write this in a certain form because we have the tools of template machinery available to us. In particular, we can do things like overloads and partial specializations and explicit specializations and so forth. So I've got this container trait struct that's templated on a container. Here I've named a type name C. I could probably have called that something a little more detailed like cont or container. And then I'm going to define a bunch of partial specializations. This is somewhat repetitive, but the nice thing is that even though it's kind of spammy in terms of actual text, what's going on here is very simple. There's no sort of deep magic involved. So even though it looks like, a page or two of code at the rather high magnification I'm running, it's really quite simple. So container traits is specialized on std vector of t and an allocator. Even though 99% of the time I'm not going to be using custom allocators myself, someone else might be using it. And because I'm writing a general erase wrapper, I would like to be able to handle vectors with custom allocators. It doesn't cost me anything to put comma A there for the allocator. And then if I have a container, if I'm being asked to get the container traits for a std vector, I'm going to say, oh, it is vector-like. So this helper struct simply has a type def. Its category type def is this empty struct that I've defined for no purpose other than to talk about its type, and it's called vector-like. I do the same thing for dec, because although vector and dec are very different containers, for the purposes of erase remove, they're both the same. So I'm going to call them vector-like. Same with list and forward list. They both behave the same to each other, so I'm going to call them list-like. And then all of set, multi-set, map, multi-map, and the unordered variants, they're all associative. So I'm going to give them the associative tag. So all I do is I have all this machinery. I could put this behind a macro or something. Macros are somewhat evil, but they can't help to avoid some repetitive text duplication. In this case, I didn't bother. And then inside my detail namespace, I'm going to write helper functions. So these are my actual implementations, and at this point, I'm going to assume that someone has told me what category of container I'm operating on. So here I've got an erase helper function that takes some arbitrary container, I don't know what it is, and some x value to erase. And I've been told that this container is vector-like. In practice, I know it's going to be a vector or dec because I provided those explicit specializations. So what this is this is a type, vector-like tag. It's a parameter. I'm being given some value. I just don't care what the value is. So I could have written over here, some value, blah, or ignore, or anything that I like. But because I'm not going to refer to it, I don't want to get an unreferenced parameter warning. So I'm just going to put the type there and omit the parameter name. That's all that's going on here. I could say int here, and I would be taking an int and doing absolutely nothing with it. In this case, taking an object of this type is doing something special for me. And then I'm going to use the erase remove idiom. So I'm going to call erase on the container, use std remove, begin, end, x, all the stuff that I explained last time. Because I'm defining this, because I would be defining this in a header, headers should not contain using directives and using declarations at file scope. Because if you say something like using namespace std in a header, congratulations, you've polluted every consumer of your header. You've dragged in namespace std whether they like it or not. Source files can say using directives and using declarations all they like, because they know that that's not going to contaminate any other source files. But headers should be clean and should not do that. So that's why I'm saying std : here, because I would be defining this code in a header. Same with erase if. If it's vector-like, I've got to call remove if with a predicate. As a bonus question, I won't cover it here. If you're curious, think about why the STL has to provide both remove and remove if for values and predicates. Why couldn't it just provide a single algorithm that would either erase values or erase predicates? Think about that. Hopefully the answer should become obvious and you'll learn a little bit about the STL. Then for list and forward list, I mentioned that I need to call these member functions that delink nodes in place. I need to call their remove member functions. In this case, it's actually doing an erasure on the value x or remove if on the predicate. And then finally, if I have an associative container, if I want to remove a single element or in the case of a map, a key, or in the case of a multiset, all the elements equal to some element, it has a member function for that called erase. However, there's no parallel erase if for the associative containers. So I need to call, in my erase if helper, an iterator loop. So I'm going to iterate through the container. Because I've got VC10 here, I can simply say auto rather than having to go get the container's iterator type and put a type name there. And then if the element that I'm looking at satisfies the predicate, then I don't want it. I'm going to erase if that's true. So I'm going to call container erase on the iterator. Now I need to be careful because when I erase an iterator, I'm going to get rid of that node and rebalance the tree accordingly. The problem is that that invalidates the iterator, just like deleting a pointer invalidates that pointer. And if I'm writing a linked list by hand, I can't increment a pointer that I've already deleted. That memory could have already been overwritten. So I need to be careful to step forward the iterator before I erase it. And that's what this little bit of code here does. When I say I++, what that's doing is it's going to take the iterator, increment it forward, so I am not going to erase what I'm standing on, and then return the old value and give that to erase, and then erase that iterator. And if you look at how all the sequence points work, if you know what those are, this is perfectly safe. Whereas if my element does not satisfy the predicate, then I want to keep it, so I'm just going to increment the iterator forward. And then finally, here I'm stepping out of my detail namespace. I'm in namespace meow, which is my library namespace. I'm going to provide erase and erase_if functions that the user will call. They take some arbitrary container, I don't know what it is at this point, and x value to erase or a predicate. They're going to call my detail function erase helper, and they're going to just pass along the container and the value or the predicate. And then they need to tell erase helper what category of container it is. So earlier I had defined that container traits machinery. Now I need to use it. So what I want to say is get into the detail namespace, look at the container traits for whatever container I've been given. This is the type container, so here I'm referring to a specialization of my template. I want to get its category type def. That's : category. And a little bit of template arcane thing here. Because I'm referring to a nested type def of something that is dependent on a template parameter, I need to say type name here in order to disambiguate things for the compiler. VC will sometimes let you get away with this, but it's best to always put that here because future versions could enforce the rule a little more conformantly. So I have to say type name, blah, 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 : category, and that's just a type. I need to construct an object of this empty ignorable type, so I'll put empty parens here, and then I'll just get a temporary object to pass along to my function. I'm going to pass it here, and then nothing's going to happen. So in fact, if I compile this optimized, the compiler should throw all of this away, because I'm not doing anything with this parameter, especially because all of this is a template in a header. It can see everything. Same with erase_if. So then I can actually use this code. I haven't shown the use case here because it's pretty obvious. If I've got a vector or a list or a set, I can say erase the element or erase according to this predicate, and everything will happen without me caring about how exactly the erasure is going on. Now, for the sequence containers, of course, erase and erase_if are linear time. They have to blast through the whole container and erase all the elements that you don't like. For the associative containers, erasing a single element, because we're calling this member function erase, is actually log time. We actually start at the root of the tree for the ordered associative containers, find all the elements that match, and then erase them and rebalance the tree. But erase_if has to look through every element of the container, so that's linear time. With the unordered containers, erasing a single element will actually be expected constant time, because we're going to hash it and then erase all the elements that satisfy the hash. So unless I have accidentally put any bugs here, this is the solution. There's other possible solutions. Instead of having this container traits machinery, I could have simply overloaded my functions on vector and dec and so forth. In this case, all the implementations are really single lines, so perhaps that would have been less code. Certainly wouldn't have needed all this container traits machinery, but I wanted to show off what it would look like if we were doing a little bit of template metaprogramming. Of course, the STL itself has far more advanced uses of this. So if you were maintaining the STL like I do, you would be writing code like this all day. So that's erase and erase_if. Today I'd like to talk about recently added components of the STL, shared pointer and unique pointer. Also a little bit of exception safety, and then at the end I've got a larger homework problem for you. So if you want to think about what you learned in part 1, I talked about the sequence containers, vector, dec, list, and the recently add forward list, which is strictly less powerful than the doubly linked list and is therefore only useful when you really, really care about space optimization. The one that you should be using like 95% of the time is std vector. But the more abstract lesson that you could take away from that is that you should use these, and you should not use new bracket bracket and delete bracket bracket. Core language provides them, and of course you've got to use them if you're implementing, a fundamental data structure of your own, or in really high performance code that is more specific, and you know something special about the problem, whereas the STL is highly general. And while it tries to be very fast for all cases, for any particular case, handwritten code could be faster. In those cases, you do need new and delete the array forms. But outside of high performance, extremely high performance, or writing a fundamental data structure, you should be using vector and deck and list and forward list because they allow you to ignore the resource management. If you array new up a chunk of memory, you have to delete it. And if something goes wrong, and not necessarily throwing an exception, but especially if you throw an exception, then you would leak that memory if you don't go delete bracket bracket it. Whereas vector and the other containers, they have destructors. So when the object, the container object, is destroyed, they're going to release all of the memory, all of the elements that they contain. So part 1 said, in effect, don't use new bracket bracket and delete bracket bracket. Now we're going to talk about shared putter and unique putter. And these are in C++ OX and VC10. Shared putter was originally from the Boost open source library. And you should be using these instead of new and delete, or giving new to unique pointer immediately and then doing nothing else with it. So this is sort of interesting. We've got these abilities in the core language to new and delete chunks of memory, and here I'm telling you not to use them. That's because they are too low level. They are newing up chunks of memory and giving you back raw pointers, just x star, where x is the type that you've newed up, and then you are expected to get rid of the memory by delete or delete bracketing it. If you forget because an error happened or because your logic was complicated, you're going to leak that memory. If you delete it twice, you'll have a double deletion error, all sorts of memory errors. Programmers have suffered for 20-something years with this stuff. If you start using classes to encapsulate your resources, either sequences of objects or individually dynamically allocated objects, then those classes will control access to it and will manage the lifetime of these for you. And the best part is, because the way C++ works with destructors, all of this happens automatically. There's no garbage collector running in the background, trying to track what memory you're using. At any particular point, the compiler knows what objects are on the stack, and as you leave each scope, it's just going to destroy whatever it needs to destroy. So it's actually quite efficient. So that's why you should be using these classes. Let's take a look at unique pointer first. Even though it is the most recently added, it's sort of the simplest to understand because it is owning a single object without any sort of reference count. So little note here, in C++ 9803, there was a class called AutoPointer, which if you've used the STL in olden days, you may have heard of. You should not use it. AutoPointer is now officially deprecated by the C++ Standardization Committee. It has severe flaws. Although it can be used properly, it's sort of a minefield, and it will bite you when you are least expecting it. In particular, it has a mutating copy constructor, which is very evil. You can think of unique pointer as AutoPointer done right. Thanks to C++ OX's R-value references, unique pointer avoids the pitfalls of AutoPointer. So I'm not going to talk about AutoPointer at all. To me, it's dead. Instead, we're going to be looking at unique pointer. So let me get rid of this example. Unique pointer and shared pointer live in the header memory because they manage dynamically allocated memory. And why don't I include IOStream and OStream? I simply cannot type. And because I'm just a helper source file, I'm going to using namespace std. OK. So the idea behind unique pointer is it is the unique owner of a dynamically allocated object. So if I have a unique putter UP, what it stores is a pointer to some object. In this case, it's a unique pointer x to some object x. And it's a smart pointer, and what that means is it is a class that imitates a raw pointer, an x star, by overloading operators. Operator overloading is good. We all know what it means to star p or p arrow member. By overloading operator star and operator arrow and other operators like that, unique pointer imitates a raw pointer and allows you to use it without horrible syntactic overhead. Okay, so let's take a look at how unique putter works. I have included the memory header, which is where it lives because it manages dynamically allocated memory. So if I declare a unique putter to int and name it up, I can new up an int and give it the value 1729. Now, I'm saying new here, but it's okay, because when I new up this int, I'm immediately giving ownership of it to the unique pointer. When the unique pointer is destroyed, it will destroy the int. So it can't possibly leak unless I do something else horribly wrong. So now I can print out what this refers to. And I'm going to want a breakpoint. Okay, so I ran my program and it printed out, the console font is small again, 1729. So that's exactly what I expected. And you'll notice here that while I said new, I didn't say delete because the destructor of the unique putter took care of it for me. If I was in a function, when I returned from the function, the unique putter would be destroyed. Now, unique putter is powered by R-value references, a C++ OX feature, and what that means is that while it's not copyable, it is movable. So I can include the utility header, which has a helper function that I'm going to need. And suppose that I have my unique putter pointing to this object x, and I construct some other unique pointer, and I want to move ownership of it to this second unique pointer. If I use std_move, as I'll demonstrate, what will happen is that I'm going to copy the pointer over, I'm going to null out this pointer, and then when this original unique pointer is destroyed, it does nothing because it contains null putter. When up2 is destroyed, it'll destroy the object. So if I construct a unique putter, I could use auto here, but I'll just say unique putter. Putter of int up2. I can construct it from std_move. Of course, I've got using namespace std there, so I can just say move of up. So what std_move is, it's a helper function that says, I know up has a name. In technical terms, it's an L value. I want to move resources out of it. So if I assign or construct from move of up, what this is going to do is it's going to null out up, it's going to null out the source, and then move the contents into up2. Unique pointer guarantees that move from objects are empty. Not all classes provide this guarantee. So if you use std_move with things like vector and dec and list, you should not assume that move from objects are empty. In fact, you shouldn't even look at them at all, except to destroy them. But with unique putter and shared putter, they're just going to contain null putters, so it's completely guaranteed that they're empty. So after this, I can test, unique putter is testable. If unique putter, the original one, is still tests as true, then that would be very unexpected, because I believe that it should be null. However, if it tests as false, which is what I am expecting, then I should see yay. And then I can print out whatever up2 refers to. And I know this one is non-null, so I don't need to test it or anything. And I should see 1729 again. So if I compile and execute this, I'm going to see, and I'm going to increase the font size here. $1729, which is the original up, and then yay, because up was nulled out after the move, and then 1729 again from up2. So I can move it from place to place. I can also return it from functions. This is actually pretty useful. The first thing you might write is a make unique function to help you construct unique putters. If I have a function returning unique putter of some x, and I'm taking stuff, I can do this. I can declare a unique putter in here, call it ret, fill a ret with something by resetting it or assigning something from it moved, and then at the end of my function I can say return ret. So with unique putter, if I went back here, I'm going to show you the compile error. If I try to construct UP2 directly from UP, I will get a compiler error because this would look like a copy construction. And I mentioned that unique putter is not copy constructible because each unique putter insists on being the unique owner of its dynamically allocated object. If I had a copy, I would have two unique putters owning the same object. They wouldn't know what to do. You could get double deletion. So this is forbidden. If I attempt to compile this, what will happen is I'll get a compiler error, and I don't see how to zoom this, but what the compiler error is saying is std unique putter cannot access private member, and it's going to complain about the copy constructor. So that's what unique putter is. If I look at the line that it's referring to in memory, that's the copy constructor. So it's saying that the unique putter is not copy constructible, but it's move constructible. Now, when I've got a function like this, unique putter, some function f returning a unique putter x, if I say return ret, you might expect I might get the same compiler error. Because I'm returning a named object, this looks like a copy construction of the return value from this local variable. Fortunately, C++ OX has a special rule. And it says, ordinarily with things like unique putter, you cannot copy from a named object. However, if you're returning a local variable, you know what? I know that local variable is going to be destroyed. So it's actually okay if we move resources out of it because no one's going to be able to see it. It's going to be dead. So if you return a local variable like this, C++ OX will automatically say std move for you, and then you can return it by value. This is very convenient. It allows you to construct dynamically allocate objects and return unique putters to them without saying std move all over the place. So unique putter is useful when you need a dynamically allocate object. One obvious example of this could be in the pimple idiom. You can look this up on Wikipedia. It's the pointer to implementation idiom, where you've got a class with a pointer to something that implements all of its methods. This is useful for breaking compile time dependencies and allowing your projects to compile faster. That's an obvious candidate for unique putter because typically you're never going to want to copy the implementation object. You simply want to store a pointer to it, and you don't want to bother with deleting it. Unique putter can take care of that for you. So unique putter is sort of the simplest smart pointer available. There's a smarter one, though. That one's called shared pointer. Until pretty recently, it was available only in the Boost open source library, which is where it was developed. Later, it was incorporated into Technical Report 1, shipped in Visual Studio 2008 SP1 under the name TR1 double cone unique putter. So if you have 2008 SP1, you do have access to this. However, if you're running Visual Studio 2010, like you should be upgrading to now, you'll have access to shared putter in namespace std and a very powerful helper function called make shared. That's only possible thanks to R-value references. So here, if I declare a shared putter, I'll show you the old style of constructing it. A shared putter to int called sp. Again, I'm going to new up an int, but I'm going to immediately hand it off to the shared pointer so everything is fine. I can now copy construct the shared putter. So I can say shared putter int sp2 as a copy of sp, and then I can print out whatever I like, both dref sp and then dref sp2. And if I compile and run this, what I'm going to get is both of the shared pointers were able to print out 1, 2, 3, 4. So what's going on here, this looks very simple. And the great thing about shared putter, just like vector, is that it is so simple to use. You only have to learn a few things about it. But it's powered by ridiculously awesome magic. So if I've got this shared putter sp and this copy sp2, what they're doing is they're owning this dynamically allocated int, whose value is 1, 2, 3, 4. This is my int. So what they do is they contain pointers to this object. Now, they share ownership of it. And what this means is that they are actually reference-counted smart pointers. When all of the shared pointers owning some object are destroyed or reset or go out of scope or so forth, then the object will be destroyed once. This is done by maintaining a count of how many shared pointers own it. So somewhere, this reference count 2 is stored. If I destroy or reset SP, who was the original owner of it, but that doesn't matter anymore, then the reference count would go down to 1. And then if I destroy SP2, the reference count would go down to 0. At that point, the shared pointer destructor says, oh, I am the last surviving shared pointer owning my object. So now is the time to delete the object. In this way, shared pointer prevents resource leaks while giving you the tremendous usability advantage of being copyable. Now, a little bit of implementation detail. This reference count isn't being stored somewhere magical. It's just being stored in a helper block. This is a reference count control block, and what it does is it maintains the strong reference count. In this case, it would be 2, and every shared pointer has a pointer to this thing. So the important thing to note is that while shared pointer is not free, it's allocating this helper object, unlike unique pointer. It's still very cheap. It's only a little object. Each shared pointer is only the size of 2 raw pointers. Again, not guaranteed by the standard, but every implementation does that. And this has some other helper machinery in it. It's only the size of a few pointers. The shared pointers will also, of course, ensure that this object never leaks if you don't do anything horrible like create a cycle of shared pointers. Shared pointer also supports the helper class weak pointer. This is useful for having a smart pointer to an object that will not keep the object alive like a shared pointer does, but can be notified when the object has been destroyed. This is useful in things like caches or to break cycles. I consider it to be relatively advanced. You can look up its documentation on MSDN or the standard, or in Pete Becker's helpful book, the C++ library extensions, a tutorial and reference, originally about TR1, but now it applies to C++ OX. So that shared pointer and its helper class weak pointer that I won't be showing. As I mentioned, in C++ OX, there is a new way to construct shared pointers. That's called make shared. You should be using this all the time when you get Visual Studio 2010, like you should already have. So I can, instead of newing up an int, I can say make shared int, and then give it some initializer. And because I'm C++ OX and I have auto, I don't need to repeat the type int here twice. I know make shared int is going to return a shared pointer int, so does the compiler. So I can simply say auto. Auto SP is make shared int, and I know it's a shared pointer. And then, of course, I can print it out, and it's going to be the same as before. drf sp. Shared pointer is also Boolean testable, just like unique pointer, all the stuff that you expect of a raw pointer. So if I compile and execute this, what will happen is I get 1729. This make shared is not only more convenient because I don't have to say new, I don't have to repeat the type twice, it's also more efficient. Through, again, awesome magic, what's happening here is because make shared, this helper function, is constructing both an object and a shared pointer to that object simultaneously, what it's going to do is it's going to store the int and the ref count control block in the same chunk of memory. So if I had an SP2, here's what it would look like. These pointers point to the int, and these pointers point to the ref count control block as a whole. Important thing to note, I am allocating only one chunk of memory, which reduces overhead. In our implementation, we're able to save some space here by avoiding some extra pointers. And then we are only calling into the allocator once. That's a Windows function. So that means fewer transitions to the kernel, fewer locks, blah, blah, blah. Make shared is essentially pure win all the time. So you should be using it to construct your shared pointers when they're available. Now, one cautionary note about shared pointer, unique pointer can be used with arrays. There is a specialization, unique pointer of X array, because it's just going to call delete bracket bracket. However, the way shared pointer works is it does not allow you to new up arrays and give you to it. If you do, what will happen is while you new bracket bracketed your array, it will call plain old delete on the array. That's an error. You should never give arrays to shared pointer. If you know what custom deleters are, you should not attempt to use them to sneak arrays into shared pointer anyways. It's a bad idea because shared pointer does not provide operator bracket bracket for index access. If you need that sort of thing and you can't use unique pointer, instead you should be using something like shared pointer to vector. That's a completely valid construct. There is more to talk about how shared pointer and unique pointer work with exceptions, but that's sort of a vast topic. I'll have to save that for a future part. As I mentioned, they do make your code extremely resistant to leaks in the face of errors and other resource management problems, as long as you use them consistently. And in this respect, they're very much like vector. The other great thing about shared pointer and unique pointer is that you can place them in STL containers. So you can say vector of unique pointer of t or vector of shared pointer of t. You can put them in maps. You can put them in pairs. All that stuff. It's very useful to be able to build up complicated data structures from just a few components lying around in the STL, rather than having to write all of that stuff by yourself. Now, let's go and look at the homework problem that I have for you for the next time. Let me stop this. So if we look at Wikipedia, okay, that is not English. There we go, Wikipedia. Okay, so the homework problem that I have for you is much larger. It's more of a homework project than the last problem, which consisted of just writing a helper function template. Here, because we've already seen vector and the other sequence containers, set and map and the other associative containers, and now shared pointer and unique pointer, we're going to combine them together and solve an actual larger problem that requires making your own data structures. So the problem I have is a game called Nurikabe. It was invented by the same people who invented Sudoku, which you've probably heard of. And you can read all about it on Wikipedia here. I've got the name here in big text for you to search on. What this is you've got a grid of numbers, and you have to fill in spaces on this grid, either white or black, according to certain rules. You can read all about the rules here. The problem that I would like to present to you is write a automated solver for Nurikabe puzzles. Now, one of the things about Nurikabe is you can prove that it's NP complete. That's a computer science term. What that means is that in general, puzzles of this sort can be exceedingly hard to solve. They can take worse than polynomial time. So that means that you won't be able to write a solver that can solve every single instance of a Nurikabe problem in a fast amount of time. You would have to guess a cell is black or white, proceed on, see if you encounter an impossibility, potentially guessing many other cells along the way. I'm not so interested in looking at that, although you should be able to write such a solver. What I'm interested in is writing a solver that can solve most instances of a Nurikabe puzzle. There are certain forms of analysis you can apply to prove that a cell is going to be either white or black. For example, in this puzzle that they've got here at the top of Wikipedia, which is actually quite ingenious, you need several forms of analysis in order to make progress on it. There's a numbered cell 1 here. The rules of Nurikabe state that when you've got a cell 1, all of the cells that are left, right, above, or below it orthogonally must be black. So without doing any guessing or backtracking, I can simply immediately color the left, the right, and the cell above this one black. There's many other rules and forms of proof that I can use to solve the puzzle. This is how humans do it. In fact, most Nurikabe puzzles meant for humans don't require ridiculous backtracking. So if you can write a program to analyze this grid and use as many forms of analysis as you can think of, and color in cells either black or white, try to see if you can solve this whole puzzle. In my own work, I'm about halfway through coloring all the cells here. I've written some data structures using the STL to analyze the grid, and I've had to use almost everything that we've talked about. Certainly the sequence, associative, containers, pair, and set, and other things like that. So it should be an interesting exercise. Post your ideas and code and requests for help in the comments, and we'll see what we come up with. Maybe you'll solve this puzzle before I do. So next time we'll look at what code we've got. I'll probably talk about exception safety, and we have many more parts of the STL to look at, including all of the algorithms, tuple, and other things. See you then.